Now we're going to tackle the definition of having a function be continuous. So a function f of x is said to be continuous at x equals c if the limit as x approaches c of f of x is equal to f of c. So in particular, you have to have the following three statements be true. First, f of c exists. In other words, c is in the domain of the function f. Second, the limit as x approaches c of f of x has to exist. And finally, the limit itself as x approaches c of f of x has to be exactly the same as f of c. So the limit has to be equal to the actual y value. So as a bit of an example, let's look at the graph of this function f of x and talk about what the function values are and what some of these limits are. So if we wanted to look at f of 6, what we'd do is we would go to 6 on the x-axis, look at the function value, and we can see here that it is going to be 0. As we look at the limit as x approaches 6 from the left of this function, it looks as though all the y values are going to 0, so it's 0. As we look at the limit as x approaches 6 from the right, again, it looks like we're going to 0 for the y values. And so the overall limit is 0 as x approaches 6. So f is continuous. You might write just CONT going forward at x equals 6, since the limit as x approaches 6 of f of x equals f of 6, which is just 0. So as long as your limit equals your function value, you're continuous. So let's look at another x value. So if we looked at f of 2, well, here when we look at 2 on the x-axis, we're not actually defined anywhere for the function. So here we say that we are undefined. If we look at the limit as x approaches 2 from the left, it looks as though the y values are going to 3. But when we look from the right, it looks as though the y values are going to 4. And so we'd say the overall limit, because those are different, does not exist. So f is not continuous at x equals 2, since the limit as x approaches 2 of the function does not exist, and since f of 2 is undefined. So we needed both of those things. We actually have neither of them, so it's not going to work out. All right, let's look at 5 as our x value. So if we look at the actual function value for 5, it ends up being 3 for the function value. So that's where you've got the filled in dot here. If we look at the limit from the left, as we come from the left, our function values approach 3, but as we come from the right, our function values are actually approaching this 5 up here. So what that tells us then is that the overall limit does not exist because the left-hand limit and the right-hand limit don't match. So f is not continuous at x equals 5, since the limit as x approaches 5 of the function does not exist. All right, and then last but not least, if we look at our function value at x equals 3, notice we've got this open circle here, so we're really looking at where the dot is. So the function value is going to be 1. However, when you look at the limit of the function as x approaches 3 from the left, it's going to actually be 2, and from the right, it's also going to be 2. So since the left and right hand limits agree, that's going to be 2. The overall limit is 2. However, f is not continuous here at x equals 3, since our limit as x approaches 3 of f of x is equal to 2, which is not the same as f of 3. So the function value is not equal to the limit. So since we don't have that, the limit doesn't exist. Or sorry, not that the limit doesn't exist, we're not continuous. Okay, so you have to be able to use the formal definition of continuity in order for us to show or prove that a function is continuous at a particular point. But you can think about it abstractly when looking at a graph as functions whose graphs you can draw without lifting up your pen. So if we look at that previous graph, if I want to draw this function, there are plenty of points where I'd have to pick my pen up if I wanted to be able to accurately draw this graph. But notice when I'm looking at this x equals 6 here, I can draw straight through this without ever having to pick up my pen. But all these other places are places where I'd have to pick up my pen, and in an abstract way, you can think of that as being where you'll end up having discontinuities. You still have to be able to do the math and show that the limit equals the function value, but you can go through that process pretty easily. So there's 3 types of discontinuities. There are what are known as removable discontinuities. And these are things where you essentially just have an open hole in the graph. And this is like when x was equal to 3 in the previous example. This is places where your limit just is not equal to your function value. So this is something where if all you did was adjust the function value to be equal to what the limit is, you could go ahead and basically fill in that hole. So think of it as things where you just have an open circle and all you have to do is find a way to fill in that circle to remove the discontinuity. There are also things called jump discontinuities. And in the previous example, this is where we had our x values of 2 and 5, and these are things where the left limit is not equal to the right limit. Not a lot we can do to fix these ones. So these are things where you've got a function value, looks like it's approaching some value on the left, and then you've got a different value, looks like it's approaching on the right. And then the last type are infinite discontinuities. And these are places where the graph has a vertical asymptote. So an example of which would actually be this next problem. So we want to use the definition of continuity to show whether or not f of x equals 1 over x squared is continuous at x equals 0. So the first thing we can see is that f of 0 here, because of this asymptote, does not exist, which immediately tells us that f is discontinuous at x equals 0. However, we also know that the limit as x approaches 0 of f of x equals infinity. So notice that on either side as we approach 0, our graph is going straight up. And so this tells us that f has a vertical asymptote. At x equals 0. So this is going to be one of those infinite discontinuities that we had talked about. So we want to go ahead and look at another example where we got a function g of x equals x squared minus x minus 2 divided by x squared minus 4. We want to know where it's discontinuous and talk about what type of discontinuities it has. So first of all, let's look at the denominator. So this is a rational function. We can factor this denominator to be x minus 2, x plus 2. So we have those two factors. So we immediately know g is discontinuous at x equals 2 and x equals negative 2. So this actually tells us right away where we have our discontinuities. The thing is, we don't actually know what type of discontinuities those are. So what we'll have to do is we'll have to go ahead and figure out if it's something where we'll have an asymptote, or if it's a removal discontinuity, or less likely it's a jump discontinuity. Jump discontinuities will happen when you have piecewise functions. So to figure out the types, what we can do is we can go ahead and factor the numerator and the denominator. So if we factor the numerator, we should be able to get x plus 1 times x minus 2. And of course we factor the denominator already as the difference of squares as x minus 2 times x plus 2. So here, what we can see is if we eliminate those, we have what essentially looks like the graph of x plus 1 over x plus 2. And this is what the graph will look like everywhere except at x equals 2. So because we could actually go ahead and remove the x equals 2 discontinuity, this means that we are going to have a hole in the graph. So this is a removable discontinuity. At x equals 2. Well, however, when we look at our other type of discontinuity, what we see is that this is already as simplified as it can be. So there's nothing else we can do to try to simplify this this potential function, and we're still going to have a value of x that makes the denominator 0, and so because of this we're going to end up with a vertical asymptote. And so what this means is that we have an infinite discontinuity at x equals negative 2. Now we can have, similar to how we've had the left limit and the right limit, we also can have left and right continuous functions. So we say that a function is called left continuous at x equals c if the limit as x approaches c from the left of f of x equals f of c. And we say that it is a right continuous function at x equals c if the limit as x approaches c from the right of f of x equals f of c. So note that f is only continuous, rather f is continuous at x equals c if and only if f is both left and right continuous. At x equals c. So similar to how we have that idea of being only having the limit exist if the left and right hand limits agree, here, as long as we have left and right continuity at x equals c, we can show that our function is continuous at x equals c. So we can go ahead and use these ideas to talk about, with this graph, whether or not the function is left continuous, right continuous, or just continuous at x equals 0, x equals 1, and x equals 2, and x equals 3. So for x equals 0, we see that f of 0 is 3, and overall, the limit as x approaches 0 of the function is 3. So f is continuous at x equals 0. When we talk about x equals 1, f of 1, it would appear, is 5. But the limit as x approaches 1 from the left is 2, and the limit as x approaches 1 from the right is 5. So it is not left continuous, because the left limit does not match the function value. However, it is right continuous. So f is right continuous at x equals 1. Okay, so now let's take a look at x equals 2. Here, f of 2 is going to be 2. The limit as x approaches 2 from the left of f of x is 2, but the limit as x approaches 2 from the right of f of x is 1. So that tells us then that f is left continuous at x equals 2. Last but not least, we want to look at x equals 3. But notice that f of 3 is undefined. So f is not continuous at all at x equals 3. Okay, so there might be some question of, are there things that we can just flat out know are normally continuous? And so the following functions, or types of functions, are going to be continuous on their domains. So we have polynomials, rational functions, root functions, exponential functions, logarithmic functions, and trig functions and inverse trig functions. So of note, they're continuous on their domains. So as long as you can go ahead and find the domain of these functions, you'll be guaranteed that they'll be continuous on those domains. Now, if you don't remember what any of these types of functions mean, our first set of notes kind of went through a brief overview of all these different types of functions. All right, we also have some nice laws of continuity. If we have two functions that are continuous at some point x equals c, then if we add the two functions, it'll be continuous at x equals c. If we subtract the functions from each other, they'll be continuous at x equals c. If we multiply the functions together, they'll be continuous at x equals c. If we take either of the functions and multiply them by some sort of real number, so this is a real number, it'll still be continuous at x equals c. And if we divide them, we divide one by the other, it'll be continuous at x equals c as long as g of c is not equal to 0. So we can't go ahead and divide by 0 still, but otherwise we'll get those continuities. Also, if a function is continuous at x equals c, and if a function f is continuous at x equals c and g is continuous at x equals f of c, then g of f of x, the composite function, which we could also write as g composed with f of x, is continuous at x equals c. And so the idea is that when you plug c into f, you're then taking whatever the function value is and plugging that into g. So g needs to be continuous at whatever that output is of the original function. All right, so let's take some of these ideas and come up or work through some examples. So we want to know where this function, g of x equals the square root of 6x plus 1, all divided by x squared minus 9, is continuous. And then we want to write our answers in interval notation. So the good news is that this is a rational function combined with a polynomial and a root function. So our main things that we know is we need to look at where the domain of this is, and it'll be continuous on its domain. So essentially we need to figure out the domain of this function. So the denominator cannot be equal to 0, and it can't have a negative under the root. So let's go ahead and check this first part. So if we want our denominator to not be equal to 0, we're looking to solve the equation x squared minus 9 equals 0. And so this, of course, tells us one thing we could do is just move over the 9 and we get x squared equals 9. And then if we take the square root ourselves, we have to remember that we're considering both the positive and negative numbers. So if we squared some negative number, we could get there as well. So here our discontinuities would be at plus and minus negative 3. For looking at our root being negative, we have to look at what's under the square root. So we want 6x plus 1 to be greater than or equal to 0, which then tells us that 6x has to be greater than or equal to negative 1, so x has to be greater than or equal to negative 1 over 6. So that might cut out part of what we're looking at, and we can look at our number line just to kind of verify what's going on here and figure out where our domain is. So we've got negative 3, we've got 3, we have our negative 1/6 over here, probably not exactly to scale, but what we know is that we have to be greater than or equal to negative 1/6. So we're only looking from here on, going this way. So everything over here we don't actually care about. So that means our function g is continuous on its domain, so that would be negative 1/6 including it, all the way to 3, unioned with 3 to infinity. All right, let's look at another example. Let's look at a few more examples. So let's say we wanted to go ahead and determine where this function was continuous and determine the type of discontinuities it has. So this is a piecewise function, so we'll want to look at all the pieces together. So here we're looking at x squared. As long as it's on its domain, x squared is going to be continuous. When we look at x, x on its domain would be continuous. And when we look at 1 over x, the only thing we'd have to worry about is when x is equal to 0. However, it's defined on a piece where x is always greater than or equal to 1. So we won't have an issue with this on its domain. This means that the only places we're going to have to worry about discontinuities are going to be where the different pieces match up. So we want to make sure that our limits on the left and right hand side match up to the function values. So since we're looking at then at x equals -1 and x equals 1, we'll want to go ahead and kind of make sure that we know what our function values are and our left and right hand limits. So if we plugged in -1, we're looking at this piece because this is where x is defined, or the function is defined when our value is -1. So f of -1 is going to be -1. If we look at our limit as x approaches -1 from the left, though, this is actually looking at the x squared part. So this will be the limit as x approaches -1 from the left of x squared, which will be actually a positive 1. However, if we did look at the limit as x approached -1 from the right, we'd be looking at the limit as x approached -1 from the right of this piece, so just x, and so here we would be looking at -1. So because of that, the limit overall as x approaches -1 does not exist, so f is not continuous at x equals -1. So this is something where it actually is right continuous, and this is something where we would have a jump discontinuity. Essentially, we'd have a function value on one lower part, and we'd have the limit on the other side going somewhere else. So left and right hand limits don't exist. However, when we look at x equals 1, first we want to go ahead and look at f of 1. So that is going to involve this piece. So that is going to be 1 over 1, or just 1. If we look at the limit as x approaches 1 from the left, that'll be looking at the middle piece here. So that'll be the limit as x approaches 1 from the left of x, which is 1, and the limit as x approaches 1 from the right of the function is going to be the limit as x approaches 1 from the right of this bottom part, so 1 over x, which is just 1. So what that tells us is that f is continuous at x equals 1. So the limit is equal to the function value. Since our left and right limits agree, that tells us, of course, that the limit as x approaches 1 of the function is 1. So they match, function value and the limit, so we are good to go. All right, now sometimes we might want to try to think about how we can go ahead and make a function continuous. So here, we don't know what c is, we have to find it. And we want to determine how we can make this function continuous. So if we have a piecewise function of x plus c quantity squared when x is less than 3, and 5x plus c when x is greater than or equal to 3, both of these are normally continuous on their domains, which shouldn't have a problem. So we really just need to find what c is that makes x equals 3 work. So we want the limit as x approaches 3 from the left of g of x to be the same as the limit as x approaches 3 from the right of g of x. So since we don't have to worry so much about the discontinuities, we'll be looking at then the limit as x approaches 3 from the left of x plus c squared, which will just be 3 plus c squared. And the limit as x approaches 3 from the right of 5x plus c, which will be 15 plus c. So we want these two to be equal. So if they have to be equal, what that tells us then is that 3 plus c quantity squared needs to be the same as 15 plus c. And so now we've got some algebra to do. So now if we FOIL this out, we'll get 9 plus 6c plus c squared equals 15 plus c. And so we want us to try to solve for c, so subtracting some things over and rearranging things, we'll get c squared plus 5c, so subtracting 1c over, and then 9 minus 15 will be minus 6 equals 0. So now we have to factor this. So when we factor this, we can get c plus 6 times c minus 1 equals 0. So our potential options for c, we actually have two. C could equal 1, or it could be negative 6. So either value for c will go ahead and make that function continuous. And you can go ahead and plug this in for yourself to verify. All right, so what's the kind of the moral of the story with continuity? So if a function is continuous, at x equals c, we can evaluate its limit by plugging c into f. So what we're saying is that we can just go ahead and if we know we have a continuous function, we can go ahead and evaluate those limits by just substituting in whatever it is we're taking the limit as we're approaching of. So if f is continuous at x equals c, then the limit as x approaches c of f of x equals f of c. All right, so we want to go ahead and evaluate the last three limits here using continuity. So first and foremost, the limit as x approaches 2 of 7x plus 2 over 4 minus x. Well, here our discontinuity is actually at x equals 4, which isn't a problem here. So since this is continuous at x equals 2, we can go ahead and just plug in the 2. So we'll get 7 times 2 plus 2 divided by 4 minus 2. So 7 times 2 is 14, plus 2 is 16, 4 minus 2 is 2, and so the limit as x approaches 2 of this function is 8. All right, next we'll be looking at the limit as x approaches 0 of 1 over 3 times the cosine of x. So when we're looking at this, we just cannot let cosine be equal to 0. So fortunately, when you plug 0 in for cosine, you actually get 1. So it's continuous here. So 1 over 3 times the cosine of 0 is just 1 over 3 times 1, which is just 1 over 3. Now, I want to be clear, when we're doing, when we're working with trig functions, unless otherwise specified, you're always using radians. So note, trig functions will use radians not degrees unless otherwise specified. Now there are things in your calculator that will allow you to switch between degrees and radians. So I know on my calculator, if I want to go ahead and switch, I have to go to mode and then where it says radian and degree, I want to make sure the radian is selected. So unless I know I'm using degrees, then I go to degrees, but typically I'll want radians. And the last thing we want is to evaluate the limit as x approaches 1 of the arctan of x. So the arctan is the same as the tangent inverse. And so arctan asks the question, what angle makes tangent equal 1? So remember, well, in this case, equal 1. So that would be, what we would have is the tan inverse of 1. And so we're asking the question, what angle makes the tangent equal to 1? Remember that the tangent of a function is just sine over cosine. And so if this is equal to 1, what we're saying is that sine and cosine have to be the same. And so what angle at which are sine and cosine the same? Well, there's an infinite amount of answers, and so the tan inverse will go ahead and choose the first quadrant angle. In this case, it will choose pi over 4. So that's our big thing with continuity, is we want to know kind of what functions we can consider to be continuous functions, and by knowing that, we can go ahead and immediately get to plug in our limits to make our lives a little bit easier.